Pluto is far away from the Sun, obviously, so the Sun is, on numerous occasions, fainter than it is here on Earth. As a result, its frigid temperatures drop to around -230 degrees Celsius during the nighttime. In a power wave, you could get as high as 170 degrees Celsius. It has an incredibly sketchy climate, excessively welcoming curious characters to an examination beyond the unmistakable areas of our planetary system. Consider the possibility that I let you in on that Pluto, the faraway and bewildering peewee planet, is finally taking its endless action, perhaps colliding with, as a matter of fact, Neptune, the ice beast. Pluto's rebellious nature has been evident from the very outset, a revolutionary on the edges of our solar system, its orbit brazenly running into another planet, challenging the common rules of planetary motion. I mean, that is no kind of direct path for a planet. Right from the puzzling intricacies of Pluto's orbit to the raised concerns voiced by astrophysical experts like Tyson and Kaku, a waiting question hangs in the vast balance: will these heavenly bodies partake in a cosmic collision? Could the intermixing of their trajectories spell unexpected repercussions for our dear planet Earth? Today, we set out on a huge journey, stacked with uncertainty, while the answers to these eminent questions could elude us. However, the potential for an accident of such endless scale serves as a stark reminder that the universe is a stage for events both striking and mysterious. Perhaps there's an alarming side, but come along with us as we dive into the intricacies of how we might decipher Pluto and Neptune, inspecting the potential outcomes of a superb clash that could reshape the delicate balance of our nearby planetary system. The stage is set, and the unfolding drama urges us to observe the confounding dance of the planets. Among other potential space calamities, the universe harbors various conundrums, and one of them is the complex conundrum known as the three-body problem. Yet scientists also expect other anticipated disasters within the cosmic theater. Although a planet colliding with another in space is especially unlikely, it isn't completely out of the question. Gravitational interactions, as described by the three-body problem, are some of the forces that affect planetary orbits. A good example of this is the TRAPPIST-1 system, which has 7 planets the size of Earth. Over time, these interactions could destabilize planetary orbits, increasing the likelihood of collisions. What's going on there, though, is that despite the fact that structures like TRAPPIST-1 are very dense, planets can impact one another's paths, especially when they are close together. Scientists constantly monitor these systems to study this dynamic and understand how planets travel through space. Another mysterious phenomenon is the rogue planets, those that float whimsically in space rather than orbiting a star. The ejection of planets from star systems can occur as a result of gravitational interactions or other cosmic eccentricities, such as the close approach of another star or the dynamic instability in multi-planet systems. Over time, these wandering planets can travel vast distances, potentially encountering other star systems on their journey. The likelihood of a planet crashing into another increases if one of these rogue planets enters a nearby planetary system. However, a rogue planet striking another planet head-on is extremely unlikely, considering how vast and generally empty space is. The sparseness of planets in open space and the immense distances between stars work to prevent frequent impacts. Still, the rarity of rogue planets is much lower than that of stars and planets in stable orbits. The star systems involved can become turbulent in the event of a significant disruption. It's highly unlikely that planets will collide head-on during these huge events because of the vast interstellar distances. The orbits of stars and planets within emerging systems can change dramatically due to strong gravitational forces. A planet could become a rogue world, freed from its star, especially when such disruptions push it out into the cold, dark depths of intergalactic space. Even so, planets could be ejected from their orbits, collide with one another, or even crash into their host stars due to these gravitational perturbations. When gas and debris are compressed under extreme pressure, gravitational correction can trigger the formation of new stellar bodies, or even cause stars to form within our solar system. The late, deep bombardment phase, which occurred over 4 billion years ago, was a time of intense impacts, involving comets and asteroids. This surge in collisions is believed to have been caused by gravitational disturbances from the outer planets. During this chaotic period, gas giants like Jupiter and Saturn were undergoing migration, disrupting the orbits of smaller bodies in the Kuiper belt and asteroid belt. As a result, these smaller bodies were thrown into erratic orbits, with many eventually being drawn into the inner solar system. This surge in impacts caused a significant rise in collisions with terrestrial planets, including Earth. While these crashes didn't involve direct collisions between planets, they highlight how gravitational interactions can result in major changes in the paths of celestial bodies. This bombardment is thought to have played a major role in shaping the surfaces and geological histories of planets in our solar system. It could have even contributed to the delivery of water and organic materials to Earth, influencing the development of life over an extended period. As stars go through changes in mass and energy, parts of planets around them could spiral inward or outward. This is especially noticeable in systems where stars are nearing the end of their life cycle. As a star becomes older and burns through its nuclear fuel, it often goes through significant mass changes, especially during phases like the red giant stage. When stars shed material in a planetary nebula, these mass changes can disturb the gravitational balance of the system, causing the orbits of nearby planets to either expand or contract. This is more likely to occur in multi-star systems, where complex gravitational interactions between the stars can easily lead to unstable orbits. In such systems, the gravitational forces from different stars can combine unexpectedly, amplifying orbital shifts. This can lead to situations where planets are captured by another star, collide with other celestial bodies, or even get flung into interstellar space. Pluto's peculiar orbit, once considered a definitive feature of the planetary family, was eventually reclassified as a dwarf planet due to its unique characteristics and orbital eccentricities. Circle the stargazing neighborhood as, however, charmed by it, and track down its spellbinding even with this modification. There's no excuse to be stressing out as to the closeness of Pluto's track to Neptune's, as shown by late figures made by conspicuous specialists like Neil deGrasse Tyson and Michio Kaku. These scientists are sounding the alarm about a grave risk to Earth, the believability of an influence between the planets. Pluto isn't typical for another planet in our solar system, and its orbit around the Sun is so unique. Pluto has not finished a full orbit since it was discovered in 1930, and its orbit takes a lengthy 248 years. The fact that it wanders off generally from the mostly round orbits of the massive planets makes its course incredibly bent, further adding to its erratic movement. Pluto also has a greater orbital tilt than many planets, with a 17 degrees inclination to the ecliptic plane, adding eccentricity to Pluto's orbital model. An interesting part of Pluto's orbit is when its path crosses that of Neptune's. For about 20 years in each orbit, Pluto comes closer to the Sun than Neptune, testing assumptions about their positions within the nearby planetary group. This leads to the question, why hasn't an accident between Pluto and Neptune happened? The explanation lies in the gravitational effects applied by other planets. The study of Pluto's orbit began shortly after its discovery, presenting a perplexing challenge for stargazers. Unlike most planets whose orbits lie roughly in the same plane near the ecliptic, Pluto's specific characteristics include a steep inclination and an elliptical shape. The mystery deepened with the realization that Pluto's orbit crosses Neptune's. This phenomenon, called the three-body problem, deals with the interactions of three celestial bodies, like Pluto, Neptune, and the Sun, and is known for its inherent complexity. In space, the gravitational effects of these bodies on each other are calculated. For Pluto, some terms that help explain this astronomical mystery include azimuthal libration, scope libration, and the VZK effect. As demonstrated by astrophysicists, azimuthal libration is crucial because it helps keep planets in their orbits. When Pluto crosses Neptune's orbit, it is no less than 90 degrees apart, a critical distance that prevents collisions. The definition applied to Pluto and Neptune, scope libration, refers to the vertical movement of a celestial body in its orbit. This ensures that when Pluto approaches Neptune or other massive planets, it is generally positioned above their orbital plane, adding an extra layer of protection against collisions. Another important concept in understanding Pluto's orbit is the VZK perturbation, named after the three researchers Van Lee, Kai, and Zuckerman. They studied the gravitational interactions between Pluto, Neptune, and the Sun. The VZK effect helps explain why Pluto's orbit around the Sun seems unusual, yet remains stable over the long term. Despite the apparent randomness in space, fundamental models and laws of motion govern the system, keeping everything in check. These factors together stabilize Pluto's orbit, preventing collisions or significant deviations from its course. The three-body problem is essential for understanding how the gravitational forces of these celestial bodies affect their motion, offering insight into the broader dynamics of the solar system. In the late 1980s, numerical simulations revealed that despite its unstable properties, Pluto's orbit is actually quite stable over long periods. Small initial deviations could lead to significant differences over millions of years, but Pluto's orbit remains remarkably secure. These findings have sparked more interest in the dynamic forces at play, particularly the effects of larger planets like Neptune, Jupiter, and Saturn on Pluto's trajectory around the Sun. Neptune's specific gravitational influence, completing 3 orbits for every 2 of Pluto, contributes to the overall stability of Pluto's orbital path. Jupiter's gravity is also significant, though less so than Saturn's. Taken together, these observations suggest that Pluto is in stable and secure motion across space, aided by the combined gravitational effects of Jupiter, Saturn, and Neptune. These forces keep the motions of celestial bodies in the universe orderly and predictable. Without these stabilizing mechanisms, the solar system would be more chaotic, with a higher likelihood of collisions and disruptions, which could have far-reaching consequences for other stellar bodies. Considering the latest theories about a potential collision between Pluto and Neptune, it is important to understand Pluto's orbit. With this knowledge, the ever-changing configuration of the nearby planetary group may be better understood. The behavior of Pluto's orbit highlights how complex interactions between orbital mechanics and gravitational forces can create apparent instability, yet still lead to harmony over long timescales. To further comprehend our place in the universe, it is crucial to observe and study these events. Space exploration often reveals the unpredictable behavior of celestial bodies, and Pluto's orbit serves as a prime example. The case of Pluto provides a striking illustration of how orbital chaos, in the beginning, can lead to stability over time. It shows that the path of a celestial body is closely tied to its initial conditions, with even minor changes in its location or speed having a dramatic impact on its long-term orbit. Scientists' ongoing study of Pluto's motion in space is largely due to virtual simulations, which replicate the gravitational interactions between Pluto and other planetary bodies, like Neptune. These simulations use complex mathematical models, helping astronomers see how small changes can significantly affect Pluto's trajectory. By controlling these models, scientists have uncovered intriguing aspects of Pluto's orbit. In the late 1980s, researchers confirmed that Pluto's orbit could still be quite erratic, though it is generally stabilized by factors like resonance and scope libration. When Pluto's position or speed deviates significantly from its expected state, its trajectory can change considerably over time. Despite Pluto's inherently unstable orbit, it remains stable for incredibly long periods, billions of years. This suggests that, despite its seemingly chaotic appearance, Pluto's journey around the Sun follows an organized order, which becomes clearer over countless observations. Understanding the behavior of planets like Pluto, which have eccentric orbits, is a significant challenge for astronomers. The intrinsic irregularity of these structures makes long-term predictions uncertain. Numerical simulations help us understand and predict the future motions of celestial bodies, but they also reveal the limits of our knowledge. These models depend heavily on accurate initial conditions and require the precise calculation of complex interactions. Even a small error can lead to entirely different outcomes, which highlights the difficulty in making precise forecasts about these cosmic systems. The wild idea of divine circles is problematic, but for example, Pluto helps us recall the ever-changing universe. While we've made progress in understanding space, Pluto's case includes our persistent restricted data in figuring out the gravitational effects of distant planets on its orbit. The Pluto circle gives critical insights into the broader components of the planetary system. It shows how each planet's presence and position can impact the stability and direction of various bodies in the system, raising concerns about potential collisions. Neil deGrasse Tyson, a prominent astrophysicist known for his work in advancing cosmology, offers a specific perspective on the puzzles within our nearby planetary system, particularly focusing on Pluto. Tyson, famous for renaming Pluto from an undeniable planet to a smaller dwarf planet, shares careful reflections on the evolving understanding of celestial mechanics and humanity's ongoing interest in the overlooked areas of space. Rather than simply focusing on Pluto's renaming, Tyson views it as a significant change that aligns with the growing knowledge about the vast array of objects orbiting the Sun. His approach emphasizes continual learning and discovery. Tyson sees the complexities of orbits, exemplified by Pluto's extraordinary path, as a constant reminder of the importance of knowledge yet to be uncovered in space. He argues that the pursuit of these countless questions is the driving force behind the exciting field of space science. Tyson also acknowledges the fundamental role of space-related events and discoveries in shaping public interest in astronomy. He considers events like Pluto's renaming and its unusual orbit as opportunities to ignite the public's imagination and curiosity about the universe. By diving into the dynamic and sometimes illogical aspects of space mechanics, Tyson opens a door for people to ponder the wonders and mysteries of the universe. Tyson has also advised the public about the potential risks associated with Pluto's erratic orbit. He has raised concerns that the three-body problem could pose a real danger, suggesting that a collision with Neptune is a plausible outcome. He highlights how such an impact could upset the balance of the solar system and lead to catastrophic consequences. A collision between Pluto and Neptune would be a rare and devastating event, releasing a massive amount of energy, likely shattering Pluto due to its smaller size and icy composition. Debris from the impact could scatter across the solar system, posing potential risks to other planets and their moons. For Neptune, such an impact could alter its orbit, depending on the specific details of the collision. Michio Kaku, a renowned theoretical physicist famous for his contributions to string theory, offers a complementary perspective on the evolving situation. His insights into the future of space exploration and the intrinsic relationship between celestial mechanics and theoretical physics provide valuable reflections on phenomena like Pluto's orbit. Kaku sees the study of Pluto and its orbit as a window into the advanced realms of space exploration. According to him, unraveling the complex gravitational relationships and orbital dynamics of celestial bodies, such as Pluto, offers significant insights for upcoming space missions. This acquired knowledge becomes crucial in navigating the solar system, anticipating potential dangers, and effectively planning missions to the outer reaches of our cosmic neighborhood. Kaku emphasizes the broader implications of this knowledge in his discussions on planetary physics. He consistently highlights the fundamental interconnection between celestial mechanics and theoretical physics, arguing that the movements of planets, such as the gravitational interactions between Pluto and Neptune, are not isolated events but rather intricately linked to fundamental physical principles. Kaku's interests in theoretical physics, particularly in the area of string theory, seek to understand these principles on a deeper level. He suggests that investigating the complexities of celestial mechanics, as exemplified by Pluto's orbit, could reveal key clues about the governing laws of the universe. Like Tyson, Kaku delves into the possibility of a cosmic collision, always fitting it into his larger theory about the universe. If Pluto and Neptune were to collide, it would be a monumental event in cosmology, providing an intriguing observational opportunity that could contribute to our understanding of string theory. String theory, a theoretical framework that replaces point-like particles with one-dimensional strings, aims to describe the fundamental forces and matter in the universe. A collision of this magnitude would offer critical data to refine and test the predictions of string theory. Kaku's perspective underscores the interconnectedness of celestial mechanics and theoretical physics, demonstrating how events like a potential collision between Pluto and Neptune could serve as opportunities to deepen our understanding of the fundamental principles governing the universe. In conclusion, the complex dynamics of Pluto's orbit, along with the viewpoints offered by astrophysicists like Neil deGrasse Tyson and Michio Kaku, highlight the intricacy and significance of celestial mechanics. Pluto's irregular orbit, potential interactions with Neptune, and the broader implications for our understanding of the universe showcase the ongoing quest for knowledge in the field of space science. Through continued observation, mathematical modeling, and theoretical investigation, we strive to unravel the mysteries of the universe and gain further insights into the fundamental forces that shape our cosmic environment.